Hello, Quantitative Methods class, and welcome to the module on normal distributions. This module, as well as the module that we'll get to in a little bit on null hypothesis significance testing, are probably the most important lectures in this entire class, because they're going to form the basis of pretty much every statistic that we're going to use. Okay, every statistic that we're going to use pretty much is going to be based off of the normal distribution. Like every single one of them is some iteration of the normal distribution. We're might be changing something about it, maybe we're using it in a different context, but all of the statistics that we're going to use in this class, except for the chi-squared statistics, are going to be largely using a normal distribution. All right, so it's important to know what a normal distribution is, what are some properties of it. So this lecture is going to be important, and then when we get to null hypothesis significance testing, that lecture is going to be like the most important lecture. Okay, so probably going to do two videos. First video is going to be on distributions in general, and then we're going to look at normal distributions and try to solve some problems with a normal distribution. Then in our next video, we'll talk about standardized scores. What are those? How do we calculate them? Again, just applications of a normal distribution. And then we'll talk about some special distributions called sampling distributions, which are going to be important for all of our studies that we do. We're always going to be looking at sampling distributions. So it's going to be important for us to pay attention to those and the properties of them. All right, what do I mean when I say distribution? All right, we previously in the last module talked about frequency distributions, but the thing that I want you to remember about those frequency distributions is we're looking at the data that we have. We're not talking about idealized data, what it's going to be like in the population. We're trying to just display the data that we have from our sample. All right, so this frequency data is going to be a little rough around the edges sometimes, right? It's not, maybe doesn't look like a perfect normal distribution, or because we're not sampling millions of people. We're just looking at whatever data set it is that we have, just trying to describe what our sample looks like. All right, so here are some examples of some frequency distributions that we looked at. Here we have a histogram, as you will recall. Here is a histogram using raw frequency. Raw frequency being just the number of instances that we've had values between maybe these couple of points. And here we have what's called relative density, which think about it just as the proportion. All right, I think about it as the percentage, the number of scores that fall between these particular values. And we can also tell that this we're looking at continuous data, probably. All right, it's not the case that these values are either 0 or 1. We can kind of see that, maybe this bar right here represents the values if it's between 0 and 0.5. This bar represents when the variable is 0.5 to 1. So we just have ye old histograms. All right, here is another example of a histogram. Again, it's for continuous data, so we're looking at reaction times, not for discrete data. And so we have what the data looks like. Now, I want you to pay attention to whatever this red line is right here. All right, this red line is trying to predict what the data looks like in the population. All right, what the data would look like in the population. So what the heck is this line doing here? I mean, it's making some kind of prediction because the data doesn't look exactly like that. The data is a little rough around the edges, but we might infer that the data in the population of reaction times looks similar to this. All right, so one thing that I want to mention before we continue, when we're looking at a continuous distribution, what is the probability of getting any one value? What is the probability of getting exactly 600 milliseconds? All right, the probability of getting any specific value in a continuous distribution. If you look here at 600, it seems that maybe it's the case that there's a decent amount of scores right there. But here's the rub. There are infinite numbers of values that a continuous variable could take. It could be 600, it could be 601, it could be 601.5, it could be 601.2, 0.52. There are infinite numbers of values. So the probability in a continuous distribution of getting any one specific value is always 0. All right, the probability is always 0. Now, there's a good chance that in this range of like 600 to 625 or whatever, there might be tons, and the probability might be pretty dramatic, might be pretty large. But for any one specific value for a continuous distribution, for a continuous variable, that probability of obtaining that one specific value is always 0. So if we want to calculate the probability, we have to have a range of values as opposed to one value. So we could easily calculate between 600 and 700 how many scores are there. We could do that, but any one value, since there's infinite numbers of values, it's pretty much going to be 0. Or it is going to be 0. There's no pretty much about it. So far we've been examining frequency distributions for our sample, for the data that we have collected. But what happens if we want to theorize about what the data looks like in the population? What does our data look like? What does our the shape of our distribution, the shape of our data, if we're looking in things in terms of like a histogram or something like that, look like in the population if we were to have everybody? All right. What we're talking about here, if we're making inferences about what's going on in the population, we're talking about probability distributions. If we're looking at probability distribution, a probability distribution is a graph. All right. It might be a histogram. It might be something very similar to a histogram that shows the frequencies in terms of probability. The frequencies in terms of probability that a value could take in the population. And another thing that's important about probability distributions is there is a mathematical formula. There is a mathematical formula that defines what the data looks like in the population. Okay, so probability distributions, we're looking at frequency, but we're looking at frequency in the population with all of the population that we're interested in. And we can have a mathematical formula that describes the graph, all right, that describes what's going on with the probability. Now, that mathematical formula might be something like y equals 2x minus 4. Maybe, but most of the time that's too simple to describe what's going on with a probability distribution. So these math equations are going to look ugly. And the good news is I don't want you to know any of those math equations. The only thing that I want you to know is that there is a math equation out there that fully describes what the probability distribution looks like. So suppose, if you would, that we're going to do a coin flip experiment. All right, and we're going to flip a coin 10 times. And we're going to calculate the probability of getting 0 heads, the probability of getting 1 head, the probability of getting 5 heads when we flip that coin 10 times, all right? If it's a fair coin, it should be a 50-50 chance. 50% it lands on heads, 50% it lands on tails. When we're looking at this, we're looking at discrete data, okay? Because it can either be on heads or it can be not on heads. So we might draw a probability distribution that looks like this, all right? So there's a 25% chance that we get 5 heads and 5 tails. There is a very, very low probability, I can't even figure out what that might be, that we get 0 heads or 10 heads. Okay, it's very unlikely. But this is the probability distribution of what this is going to look like in the population if we were to do this experiment over and over and over and over and over again an infinite amount of times, flipping 10 coins, writing down how many we've got, doing it again and again and again and again. Ultimately, when we do this near infinite amount of times, we're going to find empirically that our probability is going to look like this. All right, coin flipping is pretty easy. It's something that we can wrap our heads around. All right, now there is a formula that shows us what the data is going to look like, depending on if it's a fair coin or not, depending on how many times we flip the coin. And that formula is the binomial distribution, okay, the binomial formula. You do not need to know that, Okay, you might have needed to know that in elementary statistics if you took that, but you don't need to know that for this class. The only thing I want you to know is that there is a formula and that we could calculate using that mathematical formula what's the probability that we would get 7 heads. All right, how about if we were to flip the coin, I don't know, 50 times? What's the probability of us getting 47 heads? We can calculate that using that math equation. All right, and here's the math equation. Again, do not look at it. I know it's scary looking, but you don't need to know that. I just want you to know that there is a math formula. Probability distributions have a mathematical formula that determines what that distribution is going to look like. Now, this is a simpler experiment than what we're actually going to be looking at most of the time in psychology. This is with a discrete variable. All right, you could get 0 heads, 1 head, 2 head, 3 heads, all the way to 10 heads. You can't get 3.5 heads. All right, so what happens when we are looking at continuous data? How does this probability distribution change? All right, so let's say that we're looking at like reaction times or memory scores or anything like that, that we might have a continuous variable and not a discrete variable. So what about probability distributions for continuous variables? Well, we do a different kind of distribution. It doesn't look like this histogram right here. All right, and this special kind of way of plotting out probability is called a probability density function. Instead of having bars, we're going to draw a smooth curve. All right, we're going to draw a smooth curve, maybe something that looks like this. All right, now if we were to calculate the area underneath the curve, all right, if we were to do a little bit of some geometry and figure out the area underneath this curve, and that's the area underneath the curve to the x-axis right here. All right, the area underneath the curve for probability density function is always 1. The area underneath the curve is always 1. All right, so let me ask you a question. This is a continuous distribution. What is the probability that we get exactly 5? You should be yelling at me right now that you can't do that, or that the probability of getting exactly 5 is 0, because for a continuous distribution, anytime we're looking at one specific value, it's 0. So unlike the probability density function right here, where we can just calculate it by the height of this bar. What's the probability of getting 4 heads? 4 heads in this experiment? Well, I can go here and see that the probability is 0.2. The proportion is 0.2. We can convert this to a percentage, and it's going to be 20%. Okay. What do we do here? Now, again, we can't ask a question about what's the probability of getting exactly 5, because it's always going to be 0. So maybe we do something like this. What is the probability of getting a value between 4 and 5? Okay, we're trying to get a value between 4 and 5. Now, what we have to do for that is we need to find the area underneath the curve between 4 and 5. And if we find the area underneath the curve, and again, maybe we use a little bit of geometry to do this, this is going to give us the probability of getting a score between 4 and 5. Okay, so we want to find out if we are conducting a study and we're looking in the population, what is the probability that we would find a score, just randomly sampling people from that population, between a 4 and a 5? All right, maybe this is something like, all right, the number of seconds it takes you to answer your phone. Let's just say it's something dumb like this, okay? What's the probability that if we were randomly to sample people, that it would take them between 4 and 5 seconds to pick up and answer their phone? Well, we'd have to find the area underneath this curve, all right? How do we calculate the area underneath the curve? Now, I'm going to tell you how we're going to do this, but I want you to think, before we even get there, how would you do it right now? If I were to pay you $1,000, if you could tell me or estimate what is the area underneath the curve, how would you do that? Would you get the $1,000, or would you just stare at me? All right. But I think if I motivated you with money, maybe you would come up with an answer for this. All right. So maybe something that you can do is say, well, this is kind of like a rectangle, right? Maybe we can like draw a rectangle here. All right. And we know the formula for an area for a rectangle. So it's length times width. So the width here is 1, going from 4 to 5. And the length is 0.08. So we would say 0.08 multiplied by 1. So there is a 0.08, which would be an 8% probability that they get between a 4 and a 5. Okay, so that's maybe how you would take your first shot to see what this is like. But you might say to me, well, that's fine and good, but we are underestimating what the true probability is. All right, that rectangle doesn't fully cover this area underneath the curve. And I would say you're right, we are underestimating. It's a good guess, but maybe we need to do a different rectangle. Maybe we draw a rectangle that looks like this. Now here we might say, okay, well, the width again is 1, and the length in total, let's say it's like 0.11. So maybe there's 11% chance that we get between 4 and 5 seconds if we randomly sample one person from the population. But now you tell me, now you're overestimating it. Okay, we are overestimating the area underneath the curve. Okay, so it's somewhere between 0.11 and 0.8 or 0.08. So it's somewhere between 8% and 11%, the number of scores in the population between 4 and 5. All right, that's how you would do it with the skills that you have right now. All right, now we're going to figure this out in a different way. Okay, we're going to figure this out in a different way. If we want to find out the area underneath the curve, if we're given a probability density function, and we want to figure out what's the probability of getting a score between this point and this point. All right, we need two things. Where is it? Yeah, there we go. We need two things. The first thing that we need is the math equation. What is the math equation of this line? Okay, if we have that math equation, we can calculate area underneath the curve. All right, so maybe your math equation is something like f of x is equal to 5x minus 5. All right, that might be something that you would look at in algebra or something like that. But I hate to tell you, but a lot of the distributions that we're going to look at, we're not going to get a math equation that's as simple as this, unfortunately. We're going to get a math equation that looks a whole hell of a lot uglier than that. But luckily, we won't actually have to use that math equation. But we just need to have a math equation. Then we can calculate the area underneath the curve. All right? There's a branch of math that's all about calculating the area underneath the curve. All right? And that branch of math is integral calculus. All right? Now you tell me, hey, I've never had calculus, and that's fine. We are not going to use any calculus in this class. Okay? We're barely going to use any algebra. But I want you to know that to truly get this, to truly calculate the area underneath the curve, if we wanted to do this, we would need help with the calculus, and we would need the probability function, okay? But we've got a shortcut, so don't worry about that. But we would need somebody's help first in doing the calculus and in finding a math equation, okay? So hopefully I haven't scared you too bad right now, okay? How do we find this math equation? All right. How do we find the math equation of what the probability density function is going to look like for the population? Is it the case that we need to collect tons and tons of data? If we're looking at reaction times, maybe we need to look at thousands upon thousands upon thousands of data before we can kind of plot out what we think that distribution looks like. Okay. And if that were the case, this would be not very useful. We would need to collect tons and tons of data to get what these probability density functions would look like in the population. So that wouldn't be very useful. So what can we do? How can we solve this issue? Okay. The reason why we're so interested in this is because we are going to be very interested in what our data would look like just due to chance. We're going to be interested later on in this class, what would our data look like if there was no difference between our independent variable, or no difference between our experimental group and our control group? Is the difference that we see just due to chance, just to the natural fluctuation in the data that already exists? Or is it the case that the data, or the difference between our experimental and our control group is so great, the difference is so great, that very unlikely is it that we're going to find a difference that great due to chance? That's ultimately where we're going with this. Okay, it's going to help us with inferential statistics. But before we can get there, we need a way to estimate just due to chance, what is our data going to look like? So how do we find this distribution? And this is where the normal distribution comes in, and this is why the normal distribution is so magical. Okay, normal distributions, notice the plural here. There are many, many different normal distributions. The normal distribution is magical. I told my wife, if ever I'm getting a tattoo, I'm going to have like a normal distribution somewhere. All right, it's super cool and is the basis for the vast majority of the statistics that we use. Okay, so if we look at many things in the real world, if we look at blood pressure, if we look at height, if we look at weight, if we look at personality, if we look at intelligence, if we look at attention, whatever it is that we're looking at, the vast majority of the time, if we draw the frequency distribution, we see that the data is normally distributed. All right, here is blood pressure, systolic blood pressure. We see that it has a there's a bell-shaped curve to the data. All right, what do I mean bell-shaped? That the majority of scores are around the middle, and as we get further away from the middle of the distribution, there are fewer and fewer scores. So we have this lovely bell shape here, looking at the frequency distribution of blood pressure. Here, we're looking at the change per day in the price of oil. All right, we see here that, again, the distribution is largely normal. Here we have height in inches. And here with height, we see height is normally distributed. And these are just 3 examples. Like I said, if we look at intelligence, if we look at attention, if we look at personality, if we look at anxiety levels, all of this stuff that we're interested in turns out to be normally distributed. So if all this stuff is normally distributed, and if we can know the formula for a normal distribution, then we can use a probability density function to find out what's the probability if we randomly sample X number of people where they would be in that distribution. And it's going to be a very powerful tool for us, as we will find out here shortly. All right, so first let's talk about some properties of normal distributions. Okay, and notice here the plural. There are normal distributions. There's not a singular normal distribution. Okay, and we'll talk about why that's the case next slide. So what are some properties of a normal distribution? The normal distribution, all the normal distributions are symmetric about their mean. All right, if I were to take a line, all right, and I draw the line right through the mean, median, and mode of this normal distribution, and I were to fold it on itself, it would be perfectly symmetrical. All right, so all normal distributions are symmetrical around their mean. If we were to flip the distribution on itself, it would fit perfectly. All normal distributions are unimodal. All right, quiz yourself, see if you know what the word unimodal means. Okay, uni, like unicycle. All right, means one. There's one mode. There's one most frequent score. All right, so if we look at the shape of this distribution, the highest point should be a singular place. All right, the mean, the median, and the mode are all equal to one another in a normal distribution. Okay, the mean, the median, the mode are all equal to one another if we're looking at a normal distribution. All right, If we're looking at skewness and kurtosis are 0. All right, this normal distribution isn't positively skewed, it's not negatively skewed, it's perfectly symmetrical. Kurtosis, how peaked the distribution is, it's not too peaked, if that, sorry I'm pronouncing that weird. It's not leptokurtic, okay, it's not overly peaked. It's not overly flat, it's not overly platykurtic. The skewness and kurtosis are 0 for a normal distribution. Last property, all normal distributions are asymptotic along the horizontal axis. All right, we can think of another name for the horizontal axis. Remember from last lecture, we can call it the x-axis. Maybe we can call it the abscissa if we want to be super fancy and impress somebody. What does asymptotic mean? Asymptotic means that the graph gets closer and closer and closer, but never touches the line. All right. This normal distribution gets closer and closer and closer to the x-axis. But if we were to go further and further and further and further away, it gets closer and closer and closer, but it never quite touches it. Okay. So what would be, we're looking at these scores right here, what would be the probability that someone scores a 250 looking at this distribution? It's like over here someplace. All right. The probability of that is very unlikely, but it's not 0. It's always something slightly above 0. There is a chance that you get that extreme score. It's just very, very unlikely. It's increasingly and increasingly more unlikely that you get that extreme value. All right. Where were we? Some other qualities of a normal distribution. All right. Normal distributions can have any mean. Okay. Any mean, and we're going to call that mean mu, because that's the mean of a population. And they can have any variance, all right? So normal distributions vary in 2 ways, and that's the only 2 ways that normal distributions vary. They differ in what their mean is, where they're centered around, and they differ on their variance / standard deviation, because, you know, those are like pretty much mathematically identical to one another. Just you square it or you take the square root of it. So the variance and the mean are the only 2 ways that normal distributions differ from one another. Okay, I'm going to show, so I'm showing you this. I want you to memorize this entire thing, okay? I don't ask you to memorize much in this class, but this is something I want you to memorize, all right? This tells us the percentage of our population that is found within a given part of the normal distribution. So a mean of 0, think of this as the mean. This is mu right here on this line. All right. 1 stands for 1 standard deviation above the mean. 2 stands for 2 standard deviations above the mean. -1 is 1 standard deviation below the mean. So what is the probability that someone will score between the population mean and 1 standard deviation unit above the mean? The probability is 34, and you should know that. Again, I don't ask you to memorize much, but this is important, okay? How about if we answer this? What's the probability, if something is normally distributed, that you score less than the mean? Okay, what's the probability that someone scores less than the mean for a normal distribution? I don't actually need to look at this, and I can tell you that it's 50%. Because again, the normal distribution is symmetric about the mean. All right, so if we were to take this, half of the data points are going to be below the mean, half the data points are going to be above the mean. But if I wanted to be sure, I could count 34 plus 13.5 plus 2.35 plus 0.15 in percentages would give me 50%. Okay, I could use the graph that way. How about what's the probability that someone scores between -1 and +1 standard deviations above the mean? So suppose, let's just say that the average of a test is a 100 and the standard deviation is 15. What is the probability that someone will score between a, not 75, 85. The probability that someone would score between an 85 and a 115. That's one standard deviation below and one standard deviation above the mean. The probability would be, well, let me calculate it. That's 34 plus 34. It would be 68%. All right, this is another number that I want you to know, okay? What's the probability of scoring between -1 and +1 standard deviations above and below the mean? 68% of people will fall in here. All right, how about between 2 standard deviations below the mean and 2 standard deviations above the mean? If we were to do this math here, that would be 95% of people there. It's very unlikely that someone would get a score that's above 2 standard deviations above the mean, or below 2 standard deviations, below 2 standard deviations below the mean. All right. In fact, if you want to know like what genius is for intelligence of the people that are interested in that, it's if you can score above 2 standard deviations above the mean. So that would only be 2.35 plus 0.15, so that would only be 2.5% of the population would warrant the qualification as genius, as those individuals that care about it would label it. Okay, so one more. Between 3 standard deviations below the mean, 3 standard deviations above the mean, this is about 99.7% of people. All right, pretty much everybody. Very, very few people would score below or above this. And here's just a way to memorize it in case you're interested in this. And again, there are normal distributions, okay? Plural, because it can have any mean at all. It can have any variance at all. All right. So do we have the mathematical formula for a normal distribution? And the answer is yes. All right. And I'm going to show you that mathematical formula, but I do not want you to know it. And I do not want you to get scared when you see it because it looks ugly. Okay, we've got a shortcut in dealing with this ugly, ugly formula. Okay, so I'm going to show it to you, but please do not be scared. Here it is. Okay, this is the formula for a normal distribution. I told you it was ugly. All right, and so this is the formula for a normal distribution. Notice here that what changes in the normal distribution is whatever the population mean is and whatever the population variance is. It's going to change the graph a little bit. But this function, this mathematical formula is going to explain all normal distributions. But we are not going to use this formula. So do not pay attention to it. I'm just showing you that we have the formula. All right. So that looks scary. Let's ask some important practical questions using the normal distribution. All right, so I've showed you things theoretically, but let's go back to the real world. Let's ask some practical questions. Okay, here's our first problem. Assuming the grades on a test are normally distributed and the class average for our history exam is 75 and the variance is 225. You make a 90 on the history exam, so good job you. What is the percentage of classmates that scored worse than you? This is an important question, right? We might be interested into this. If we know that the scores on the history exam are normally distributed, and we have the variance, and we have the population mean, can we calculate this? And we can. First thing that we want to do is we need to convert this variance to a standard deviation. So we need to take the square root of it. So first thing that we're going to do, we're going to take a square root of 225, and it gives us 15. It's almost like I picked a number where it was going to work out nicely. I did. Okay. How many standard deviation units are we above or below the mean? Well, the mean is 75, as we see here from the problem. And a 90 is 15 points above 75. So we are 1 standard deviation unit above the mean. So we're right here on the normal distribution. How many people score less than this? Well, I can calculate 34 plus 34 plus 13.5 plus 2.35 plus 1.5, okay? And that's going to give me the percentage. which is going to be 84%. All right, I can actually calculate this a little bit easier. I know that there is 50% of people that score below the mean. And we're 1 standard deviation unit above the mean. Okay, the difference between the mean and 1 standard deviation unit above the mean is 34% of the population. So that's 50% plus 34%, which is going to give me 84%. All right, this is a rough approximation. All right, this is a rough approximation of what's happened, but if we know that the data is normally distributed, we can come up with an estimate, and most data is normally distributed. Okay, how about if I were to ask you about the probability and not the percentage? How about if I was asking you about the proportion? All right, you change that 84% to 0.84. That's what you would need to do, okay? Because again, you can convert between percentage and proportion by either multiplying it by 100, that's how you convert a proportion to percentage, or dividing by 100, that's how you go from percentage to a proportion. Just a little bit of review there for you guys. All right, let's ask another question. Okay, again, same history test. We have the mean of 75, the variance of 225, which of course would mean the standard deviation was 15. How many students in a 200-person class failed the exam? Okay, how many people failed the exam? Well, first we need to calculate what is failing. Okay, let's say that below a 60 is failing. Okay, below a 60 is failing. All right, what is the 60? Okay, 60 is 1 standard deviation below the mean. Remember, the mean is 75. The standard deviation is 15. 75 minus 15 is 60. So if you score lower than a 60, if you score in this range, all right, you are failing the exam. So the first thing we need to do is find the percentage of the class that fails the exam. So that would be 0.15 plus 2.35 plus 13.5. All right. And if we were to add all of these together, the percentage of students that's failing the exam is 16%. Okay, 16% of the students. If we do that math here quickly with this lovely graph that we memorized. All right, so 16%. Now, it's a 200-person class. So what's 16% of 200? All right, turns out that it's 32. How did I do this math? Okay, I converted 16% to a proportion, which would be 0.16. And I multiplied 0.16 by 200, and that gives me 32. So I just want to make sure that I'm talking about what I'm doing for my math here. So approximately 32 people will fail the exam in a 200-person history class. All right, again, this is an estimate, okay, because we're using a limited number of people, not infinite numbers of people. Okay, so you guys should be able to conceptually understand what we're doing with these problems. Okay, we're using this table. It's working out wonderfully for us. But so far, it's almost as if I've rigged the problems to give us 1 standard deviation unit above the mean and 1 standard deviation unit below the mean. What happens if we are 0.43 standard deviation units above the mean? Ooh, I didn't tell you to memorize something where that would help out. What happens if you are 0.12 standard deviation units below the mean? We don't have the percentages there. Do we give up and throw our hands in the air and say, I can't do this problem? No. If data gets messy, there's something that we can do. All right. So what I showed you here is a good conceptual example of these kind of problems. But doing them in practice, we're going to do something else. Okay. What are we going to do when data gets messy? So there's many different kinds of normal distributions, as we talked about before. Their means might be 50, they might be 100, their mean might be 2.56789. Okay, the mean could be anything. The variance could be anything. So the first thing that we need to do is we need to convert our normal distribution to a standard normal distribution, a normal distribution that's always the same. All right? And we're going to call this normal distribution the standard normal distribution. The standard normal distribution is a special singular normal distribution that has a mean of 0. It always has a mean of 0 and has a standard deviation of 1. If it has a standard deviation of 1, what's its variance? All right. 1 multiplied by itself, 1 times 1 is 1. So the variance and the standard deviation are the same thing for the standard normal distribution. Okay. So what we're going to do to answer our problems, okay, we're going to take this standard normal distribution and we're going to take whatever normal distribution that we have and we're going to convert our data to the standard normal distribution. And then we're going to utilize a table based off of the standard normal distribution to help answer our problems. Okay. We will use a table to help answer questions about the standard normal distribution. But the first thing that we need to do is we need to convert our data to the standard normal distribution. How do we do this? We do this by calculating a z-score. So a z-score is a standardized score. More about what that specifically means in the next video. For any normal distribution or any normally distributed data. Okay, but it has to be normally distributed for us to make use of the z-score. Okay, z-scores, if we convert all of the scores in the population to z-scores, the mean of the z-scores will be 0 and the standard deviation of the z-scores will be 1. So all of the z-scores will conform to that standard normal distribution. All right, so how do we convert a score to a z-score? Well, this is what we do. Okay, we take the score, that's what x is, and we subtract it from the mean. Okay, we take a score, we subtract it from the mean, and then we divide it by the standard deviation. So we take a score, subtract it from the mean, and then divide it by the standard deviation, and that's how we convert a score from a normal distribution to be a z-score. Let's do an example here. So you take a test of extroversion, and let's say that there are 20 questions about extroversion, and you either answer the introverted way or you answer the extroverted way. So you score 16. The mean on the test is a 14, and the standard deviation of the test is 5. What is our z-score? We have to convert this data to a z-score. Well, we're going to take our score, 16, and subtract it from the mean. 16 minus 14 is 2. Okay, we're going to take 2 and divide it by the standard deviation of these scores. The standard deviation of these scores in the population is 5. 2 divided by 5 is 0.4. Yay, I did the math correctly. I got to be careful sometimes. Who knows what was happening when I was making these slides? I might have made a mistake. So 2 divided by 5 is 0.4. And like I said before, 0.4 is not here. What are we going to do? Oh no. Luckily, we have a table. Okay, we have a table that gives us the answers. We could, if we really wanted to, use calculus and that ugly formula that I showed you for a normal distribution and come up with the answer. But nobody has time for that. You don't want to do that. I don't want to do that. That would take far too long. We've got a much easier alternative. Let me show you. All right, this is what I am going to give you guys. I'm going to pass this out in class. You also have one in the back of your textbook. This is a table for a standard normal distribution. For any particular z-score, we can find the proportion of people that score higher than that value and the portion of people that score lower than that value. Okay? So our z-score was 0.40. So let's look at this up in this table. Okay? We're right here. Okay? Now there's two numbers. There's the larger portion and there's the smaller portion. What exactly do these numbers mean? Okay, let's go back to the beginning here. All right. This is the larger portion, this is the smaller portion. If we have a z-score of 0.40, it's to the right? Because remember, the mean of the z-score is a 0. So it's going to be over the right here, 0.40. So the smaller portion is going to be the proportion of people that score above that z-score. And the larger portion is going to be the proportion of people that score below that z-score. So let's go back here. Okay. So the larger portion, which again would be the proportion of people that scored lower than that value, is 0.65542. The proportion of people that score higher than that value is 0.34458. All right. Look, we used the table. We didn't have to do any algebra. We didn't have to do any calculus. We just looked it up. All right. Okay, where were we? Oh, it was the percentage of people that scored lower and higher. Okay, I'm converting those proportions to percentages here. I'm multiplying them by 100. So roughly 65.5 people scored lower than you on that test of extroversion. 34.5% of people scored higher than you on that test of extroversion. The reason I'm showing this normal distribution function here is we could have used it, all right? And the way that we actually came up with those values on that table was using the calculus. But you don't want to do that. I don't want to do that. If I were, I could not, I don't think. Okay, I don't think I could do the calculus to get the right answer. I'd have to look some things up. Maybe I could do it, but it would be a pain. It's been a long time since I did that kind of math. Okay. So we can look up in the table to answer questions like this, okay? If our data is normally distributed and I give you the population mean, I give you the population standard deviation, we can find out the percentage of people that score above and below the mean. Let's do a couple more problems here to make sure that we have a good grasp on what's going on. All right, we've got our old friend Eeyore here, and Eeyore is taking a test to measure happiness. And he scores a 2.5. Okay, the mean on the happiness test is 10. Who would have predicted that Eeyore was low on the scale of happiness? And the standard deviation of this happiness measure is 5. So how many people / imaginary animals score lower and higher than Eeyore? So the first step to do one of these problems is to convert the score to a z-score. So we have 2.5, and we're going to subtract it from 10. And we're going to divide that by the population standard deviation, which is 5. So 2.5 minus 10, this is going to give us negative 7.5. Negative 7.5 divided by 5 gives us negative 1.5. All right? So now we can go to our table and find out how many imaginary animals score above and below Eeyore on our measure of happiness. But we'll run into a problem. All right. If I look at my table, there are no negative values. Oh no. Is my table busted? Should I have given you another table? Now the answer is no. We have everything that we need using this table. We're going to rely on a special property of the normal distribution. The normal distribution is symmetrical. It's symmetrical about its mean. So we should be able to look up the score for positive 1.50 and use these values to help answer our question. Originally, when we first did this problem with the extroversion, let me scroll back up here. The smaller proportion, or the smaller portion, indicated the percentage of people that scored higher than the particular value. The larger portion was the percentage of people that scored lower than the particular value. All right, but luckily for us, if we can use the same logic to find out what to do for a negative z-score. All right, Suppose, if you would, that instead of having a positive z-score, let's say that this was positive 1.5, we have negative 1.5, okay? And so it will be somewhere here. Do I have a pen or like a, yeah. No, that's bad. Don't do that. Go back. No. Line? Okay, this is working out horribly bad. But suppose we had a line here, all right? Now, wait a minute. Give me 1 second here. I thought I might have had something where I can mark. Give me 1 second. All right, my apologies for that. I thought I might have had a tool, and I don't think I have the tool. I think they might have changed up my Zoom. All right, but suppose we have a line right here. All right. The smaller portion this time is below. The smaller portion this time is below for these people. And the larger portion is above that, okay? The larger portion of people is going to score above that negative z-score. All right, a smaller amount of people are going to score less than that particular z-score, just the way that the normal distribution works out. So let's go back to our table right here of 1.50. For positive 1.50, 93.319% of people score less than that value. And 6.681% of people score above that value. Now we're going to flop those when we have a negative z-score. For the negative z-score, 93.319% of people are going to score above that negative z-score. And 6.681% of people are going to score below that z-score. All right, so that's how we can use the same table to operate with negative z-scores. All right, so where is negative 1.5 on the handout? It's not there. Normal distributions are symmetrical, so we look up 1.5. So this means that roughly 6.7% of imaginary animals score lower than the value. 93.3% of imaginary animals score higher than negative 1.5, okay? And think about it. Eeyore is a pretty depressed donkey. He's not feeling too good about himself, okay? There's probably a lot of imaginary animals that score higher than him on a measure of happiness, all right? Very few imaginary animals score lower than Eeyore on happiness, all right? So, additional benefit of using z-scores is that we can make comparisons of different tests. So suppose you and your buddy took an entrance exam to get into college. Maybe you took the ACT and your buddy took the SAT. So I've got Ted, and Ted's a bit of an a-hole. And Ted scored a 1,625 on the SAT. And he thinks he did better than you because you scored a 25.6 on the ACT. Now, both of these come from a normal distribution, okay? The mean of an SAT is 1,500. The standard deviation is 250. The mean of the ACT is 20.8, at least it was the year when I looked this up. And the standard deviation of it is 4.8. So let's try to see who actually did better on their standardized test. Is it you or is it Ted? So what we're going to do is we're going to convert both of these scores to z-scores. All right, so we're going to take Ted's first. We're going to take 1,625 minus 1,500, which is going to give us 125, and divide it by the standard deviation, which is 250. All right, I was nice with this problem, and I gave you the standard deviation. Sometimes I might try to trick you and give you the variance. So be mindful of this. If you've got the variance, you can use it. You just have to convert it to a standard deviation first. So we have 125 divided by 250, and this is going to give us 0.5. So Ted's z-score is 0.5, which is admirable. It's above the mean. Well, let's see how you did. You scored a 25.6. The average on the test is a 20.8. So this gives us 4.8. And the standard deviation of the test is a 4.8. So that means you have a z-score of 1. You did better on the SAT than Ted did on the SAT. All right, we can convert both of those tests that have different means, different standard deviations, and convert them to a common metric. Okay, especially if these tests are measuring the same thing, which for the most part the SAT and the ACT are measuring the same thing. They like to make out that those are different, but really there's not much of a difference. Okay, so you did better on the ACT than Ted did on the SAT. All right. Couple more problems. Okay, these z-score problems, these normal distribution problems are going to be important for us. So a company is going to hire employees, and they are only using a test of integrity to make their decision. Okay, some companies have integrity tests. So they decide to hire anybody with a test score of 30 or higher. The mean of the integrity test is 20, and the standard deviation is 4. Out of 350 people that apply for the position, and we assume that integrity is uncorrelated with interest in the job, how many people will be hired? So with any of these problems, the first thing that we need to do is to find the z-score. So we're going to take our score, which is 30, and subtract it from the mean. 30 minus 20 is 10. Okay, 10 divided by 4. All right, 10 divided by 4 is 2.5. So our z-score is 2.5, and we're trying to find the percentage of people that score higher than 2.5. Well, luckily I've got a table. Let's go back to it. Let's find our 2.5 here, okay? What's the percentage of people that score above a 2.5? All right, it's the smaller portion because we're using a positive z-score here. So 0.00621 proportion of people score higher than a 2.5 z-score. If I were to convert this to a percentage, this would be 0.621% of people score above this. All right, so let's go back to our problem with this handy dandy information as I channel my inner Blue's Clues. I don't know if you guys are too young to remember Blue's Clues, but I don't know why that reference popped up. All right, so this is about 0.6% of people are going to be hired. 350 people apply for the job. So this is we're going to convert this back to a proportion. So 0.006, and we're going to multiply it by the number of people, which is going to give us 350. Okay, 350 people are going to apply to the job. What is 0.6% of those people? Well, we'll do this multiplication, and we find that it's 2.1. Now, you can't have 1/10 of a person. This just doesn't work out. So we're going to round it, okay? approximately 2 people out of everybody that applied will be hired for the job. Okay, we'll have a high enough score on this integrity test to be hired. So this is just like every other z-score problem, but we have an additional step. We have to multiply the proportion by a number of people. So the number of people that have this particular score, we can do that calculation. Okay, here's the hardest z-score problem you're going to get. How many people score between a 16 and a 20 on that integrity test? Ooh, instead of using, do I have my normal distribution? There we go. Okay, so we've got our normal distribution. Instead of finding a certain z-score and then calculating how many people are above it, how many people below it, we're doing something slightly different here. Okay, we're doing something slightly different here. All right, we have to find some portion within this z-distribution. So maybe it's between this value and this value. So how are we going to do this? We're going to use some subtraction to do this. So let's say that the 16, well, first thing that we do before we begin this problem is we need to find the z-scores. So a 16, okay, the average on the test is a 20. So 16 minus 20 is a -4. -4, okay, -4 divided by 4 is going to give us a -1. Okay, it's going to be a -1 z-score. How about if we have the 20? Well, 20 minus a mean of 20 is going to give us 0. 0 divided by 4, we're going to get a z-score of 0. All right. So this is what I'm going to do. All right. Essentially, I'm trying to find the percentage of people that scored between a -1 or 1 standard deviation unit below the mean, and the percentage of people that score right at the mean. Okay. Now, knowing my table, I already know the answer to it. It's right there. It's about 34%. Okay, but let's say that this was something else. Okay, what I'm going to do is I am going to use subtraction to get at this. I'm going to go to my table and I'm going to find out what is the percentage of people that score lower than a z-score of 0. Okay, I'm going to find that. And I'm going to subtract that from the percentage of people that scored lower than a z-score of -1. All right. I'm going to look at my table, and I'm going to find the proportion of people that score below a z-score of 0, and that's going to be 0.5. It's going to be 50% of people. No duh, it's the mean. Okay, 50% of people are going to score above the mean. 50% of people are going to score lower than the mean, according to a normal distribution. All right, I'm going to look at my table for a z-score of -1 and find out the percentage of people that scored lower than that. Let's go back to our table here. Now again, I can't look up -1. I've got to look up +1. So let's do that. Okay. What is the proportion of people that score lower than a -1? Okay. It's going to be this one over here. It's going to be 0.15866. Okay, that's the proportion of people that are going to score lower than a -1 z-score. All right, let's go back to the slides. Okay, so I rounded it a little bit, and we have 0.50 minus 0.159. Essentially, what I'm doing is I'm finding the percentage of people that scored less than the 0 z-score and the percentage of people that scored less than the -1. So I'm finding all of this, and I'm subtracting it from just this part, which is going to leave me with just this part right here, which is the answer to the question. Okay, the number of people, the proportion of people that scored between a 16 and a 20. It's going to be the proportion of people right here. All right, when I do this math, I get 0.341. That's the proportion. If I want to convert that to a percentage, this is 34.1% of people. okay? If I want to find out how many people are going to score between a 16 and a 20, I've got to multiply the proportion that we found by the number of people that applied. So we have 0.341 multiplied by the total number of people that applied for the job, which is 350. This is going to give us 19.35. We can't have 0.35 of a person. So approximately 119 people scored between a 16 and a 20. Okay, so that's how we're going to do this kind of problem. All right, I just wanted to show that to you guys. We're going to do a decent amount of these problems, and hopefully with the homework, hopefully with the recitation, you will understand what's going on. All right, but I just want to go through our problems and talk about normal distribution in general. Like I said, this lecture is pretty important. All right, I hope that made sense. I hope you guys enjoyed the lecture, and I hope you guys have an amazing day. I will talk with you later. Bye-bye.